press the bell icon on the YouTube app and never miss another update.
Today we are going to discuss the part 7 class of oscillation. So in the previous class we have discussed about restoring force. Generally, whenever a body is in its mean position or equilibrium position, sometimes a force displaces the position of the body or a particle, and sometimes the body may comes to its initial position or equilibrium position. When the body comes to its equilibrium position, in some cases, again a force is required. First one, the force which displaces the body from its equilibrium position. Then to come back to its original position, equilibrium position or mean position, right, again a force is needed. Any force that brings a body back to its original position or mean position, equilibrium position after the removal of displacing force is called restoring force, right? Even whenever a body is executing simple harmonic motion, right? Usually we take the case of a simple pendulum at rest. When a simple pendulum is at rest, no force is acting on the body. In fact, the net force acting on the bob of the simple pendulum is 0, right? That means downward weight of the bob is balanced by upward tension in the suspended string, right? Now in that case, net force is 0, there is no oscillation in the bob. When the bob is taken in hand, slightly displaced, right? Now that force is called displacement force, that changes the position of the bob from its mean position to certain displacement. When we leave that bob, now the displacement force becomes 0. Now the bob goes to its mean position or it moves towards its mean position. The force that causes motion of the bob towards its mean position is the restoring force in that case, and due to that restoring force it began to oscillate, right? So the oscillational motion of a body or simple harmonic motion of a body is due to a restoring force acting on the body, right? Now there may be different restoring forces acting on different bodies, right? But here our discussion is confined to a restoring force that causes, right, simple harmonic motion in a body, and we have derived this equation. So F is equal to minus m omega square y, right, where m is mass of the body executing simple harmonic motion, omega is angular velocity of the body, that is equal to 2 pi f or 2 pi by t, and y is the displacement. The negative sign in this equation indicates, right, the force always acts towards the mean position, right? Now we see in a simple harmonic motion, displacement is a vector quantity. The direction of displacement is always from, right, mean position or away from the mean position, right? But the direction of force is always towards the mean position irrespective of direction of motion of the bob. I mean to say, whether the bob is moving away from the mean position or towards the mean position in positive direction or negative direction, the restoring force always acts towards the mean position. That is the significance of this negative sign here. But when we consider only the magnitude of the force, that force F is equal to m omega square into pi. For a given body, m is constant. For given simple harmonic motion, omega is constant. That means from this equation, the force is directly proportional to displacement. Right? It is a very important concept. Right? Now we will take forward this concept. Right? From this equation, F is directly proportional to y. The restoring force is directly proportional to displacement. So, more the displacement of the body from its mean position, more will be the restoring force acting on it. Right. Now, we will take another concept, force constant, denoted by the symbol K. Right now, the experiments have showed that, right, the magnitude of restoring force acting on a body, right, is always directly proportional to displacement of the body from its mean position, right. For example, we take the case of a spring. It is in original length L. Suppose we attach a body of mass M. Then what happens? Then when we attach a body of mass M, the spring gets stretched, say like that. So M. Now, what is the force acting on the spring? It is mg in vertically downward direction. Now, a force, restoring force F comes into play, and that acts in vertically above in the opposite direction of weight. Here weight acts as the displacing force, right. Now here the length of the spring is increased by L. It gets expanded or it is displaced, right. Now here if we go on increasing the mass or increasing the weight, what will happen? Right, the length small l, that is the length through which the spring gets stretched, also increases. Right, say we have a simple pendulum in its mean position. Suppose it has to be displaced through a distance of 5 centimeter, say, and next case it is displaced through a distance of 10 centimeter. What is the difference in displacing it through 5 centimeter and 10 centimeter? When we displace it through a 5 centimeter, we have applied a small force. To displace it through 10 centimeter, we need to apply more force. To displace it through 15 centimeters, still more force is required. So as the applied force increases, again the restoring force also, right, increases, right. So from these observations, it is clear that the restoring force developed in a body is directly proportional to displacement of the body from its mean position, right. So more correctly we can say that the restoring force acting on a body executing simple harmonic motion at any instant of time is directly proportional to displacement of the body at that instant of time. That means we can say, right, here restoring force is directly proportional to displacement of the body, or the restoring force F is directly proportional to Y, right? Suppose if we have a body, simple pendulum in its mean position. Suppose the body has a displacement at any instant of time t. Now the restoring force F acting on the body in the absence of external displacement force, it is directly proportional to, right, displacement, right? If we increase the displacement, we need to apply more displacement force and there will be more, right, restoring force. So F is directly proportional to Y, we can write, or we can write F is equal to minus K into Y. Let us take it as equation number 1. Let us take it as equation number 1. Here we have two things here. One, that is a negative sign, right? The negative sign indicates that, right, F is always directed towards the mean position. The significance of negative sign is that it is always directly directed towards the mean position, like here, right? Now K is a proportionality constant. Proportionality constant, right? Or in the case of spring, it is called as spring constant, right? Now, greater the value of K for a spring, even the restoring force developed in a spring when it is stretched by an external force is also F is equal to K into Y, where Y is the distance or the length through which the spring gets expanded, and K is called force constant or spring constant, right? Now, in case of particularly spring, right, if the value of K is high, then the spring is more stronger. If the value of K is less, then it is a weak spring, right? We are using springs in different occasions, right? Let us take two cases. In a ball pen, jetter pen, we are using the spring to, right, open the nib of that pen, right, or that nib of that what we call that refill, right? Now we are using a spring there. At the same time, we are using the spring in motorcycles at the back of the seat, right? We are having shock absorbers. You might have seen they are nothing but springs associated with the other equipments. Mainly it is the spring, right? Now spring takes the shock. It is due to the impulsive force, that is impact, which we have studied in Newton's laws of motion. What is the difference between a spring? used in a motorcycle, right, as a shock absorber. And again a spring, that is used in spring. It is easier to, right, stretch or compress a spring that is used in a pen, but it is not that much easy to compress or expand a spring that is used in a motorcycle. So we say that the spring constant or force constant is high for that spring used in motorcycle. That is, it is a strong spring, and the value of K is less for the spring that is used in pen, right. So we say that it is a relatively a weak, right, spring. That's all about the spring I am talking. But this equation is in general, right, for any body executing simple harmonic motion, F is equal to minus Ky, right. And when we consider the magnitude of force, right, now magnitude of restoring force, right, F is equal to K into Y. Let us take it as equation number 2, right. Now just we have neglected the negative sign because it is indicating only one fact, that is force is directed towards the mean position, right. So this is the magnitude of restoring force. So from equation 2, right, we can write K is equal to F by Y, right. K is equal to F by Y, or K, that is the force constant, is equal to, it is the magnitude of restoring force by magnitude of displacement. Magnitude of displacement. Let us take this equation as equation number 3. So when Y is equal to 1, that we call it as unit displacement, then the value of K is numerically equal to F. Numerically means only the number involved in the value of K is equal to number involved in the value of F. That is means numerically equal because they have different units. K has different unit and F has different unit, but their numerical values are same, right. So therefore force constant is defined as the magnitude of restoring force per unit displacement. That is, right, it is force constant, right, is defined as restoring force. In fact, magnitude of restoring force per unit displacement, right. There is a definition of K. Now what is its SI unit? Now SI unit of K is Newton per meter. Its SI unit is Newton per meter, and this K value, force constant value, plays a very important role, right, in case of simple harmonic motion. Now the time period and frequency of simple harmonic motion, it depends upon the value of K, that is the force constant. What? Period of simple harmonic motion and frequency of simple harmonic motion, both of them depend on the value of K. That's why it is very important. Even when we obtain expression for time period and frequency, right, that involves this k, that is the force constant, and that's all about this force constant, right. Right. Now we will discuss some facts here. So we have that restoring force F is equal to minus ky, we have discussed earlier, and in the previous class we have discussed restoring force. We have that restoring force F is equal to minus m omega square y, that is equation 2, right. Again we take the case of a simple pendulum, right. It is oscillating about its mean position, right. Now this is a restoring force, right, F displacement y, right. This is angular displacement theta, omega is equal to theta by t, or it is equal to 2 pi by t, or is equal to 2 pi f. We have already discussed the relation between angular velocity, time period and frequency, right. So here m is mass of the body executing simple harmonic motion, omega is angular velocity, and y is displacement. Now comparing equations 1 and 2. Comparing the equations 1 and 2, right, we will get k is equal to m omega square, right. So comparing these two equations, we get k is equal to m into omega square, right, or omega square is equal to k by m. I will take this as equation 3. In the next course of the discussion, we are using this relation. Remember this relation: in simple harmonic motion, omega square is equal to k by m, or this omega is equal to square root of k by m, where m is mass, k is force constant, right. Now here, see it here, this omega is equal to 2 pi by t, omega is equal to 2 pi by t, therefore 2 pi by t is equal to square root of k by m, right, or equating this one, we have t is equal to 2 pi into square root of, right, m by k, right. It is a very important equation. In general, for any body executing simple harmonic motion, right, the time period of simple harmonic motion t is equal to 2 pi into square root of m by k, where m is mass of the body executing simple harmonic motion and k is a force constant, right. Using this equation, we can derive the time period for, right, a loaded spring, as well as we can derive an expression for time period of a simple harmonic motion, that means simple pendulum. Remember this equation, right, t is equal to 2 pi into square root of m by k, right. Now right, now we have period of simple harmonic motion, period of simple harmonic motion, t is equal to 2 pi into square root of m by k, where m is mass, k is force constant, right? Or right, this t is equal to, right, 2 pi into square root of m, right? Now we have k is equal to f by y. Now replacing k by f by y, we get t is equal to 2 pi into square root of m by fy. Now this is equal to square root of, right, 2 pi into square root of, right, this y goes to numerator, right? Now m by y, right, and here this f is equal to ma according to Newton's second law of motion, where a is the acceleration of the body executing simple harmonic motion. So here mm get cancelled. Here I will take it as equation 1 here. So therefore, now another equation for period of simple harmonic motion. So t is equal to 2 pi into square root of y by a. This is equation 2, or we can write period of simple harmonic motion is equal to 2 pi into square root of displacement, right, by acceleration of simple harmonic motion, right? So this is the time period in terms of k, and this is time period in terms of displacement and acceleration. Now while dealing with the competitive examination, we should know every relation between physical quantities of that particular concept. Here we have the relation between time period, displacement and acceleration of simple harmonic motion, right? And we know that frequency of simple harmonic motion is the reciprocal of time period. Now frequency of simple harmonic motion f is equal to 1 by t. Therefore write now frequency of SHM, frequency of simple harmonic motion, f is equal to, taking the reciprocal of time period, that is t is equal to 2 pi into square root of m by k. We have 1 by 2 pi into square root of k by m. This I will take it as equation 3, this I will take it as equation 4. This expression gives the frequency of simple harmonic motion. Remember that earlier I told you, right, both time period and frequency, they depend upon the force constant k. Or again we have frequency of simple harmonic motion f is equal to, right, 1 by 2 pi into square root of a by y. Remember that equation 2, t is equal to, right, 1 by 2 pi into, right, square root of t is equal to 2 pi into square root of right y by a. Therefore here it is 1 by 2 pi into square root of this is right, a by y. This is equation 5, right. So again I will tell you, remember those two equations, right. That is 1 omega square is equal to k by m. In the next concept I am going to use this relation, as well as t is equal to 2 pi into square root of right m by k. These two equations, right. So the thing is here, what is this equation t is equal to 2 pi into square root of m by k? It is the period of a simple harmonic motion, right. It is period of simple harmonic motion. Where it can be applied? It can be applied to any body that is executing simple harmonic motion. How to identify that a body is executing simple harmonic motion, right? How do you identify that a body is executing simple harmonic motion? Because we have some characteristics of simple harmonic motion, like number 1, it is a periodic motion. Number 2, magnitude of acceleration is directly proportional to mean position, right. Number 3, the direction of acceleration is always towards the mean position, and of course the motion is to and fro motion about its mean position, right. Now among the 4 characteristics, the 2 important characteristics is A is directly proportional to y, or we have shown that A is equal to minus omega square y. When we are observing a motion, right, whatever it may be, if the acceleration of that motion, right, comes out to be A is equal to minus omega square y, then it is definitely a simple harmonic motion, right. So when a particle has an acceleration which is given by A is equal to minus omega square y, right, then it is a simple harmonic motion. Now in that case, that period t is equal to 2 pi into square root of m by k. Is that clear? What I am telling is, we have the expression for time period of simple harmonic motion. To apply this equation, right, to find the period of a motion, right, we have to ensure that it is a simple harmonic motion. Then only this equation is applicable. How to ensure that motion is a simple harmonic motion? It is a simple way. Find the acceleration of the particle. If A comes out to be equal to minus omega square y, we know the symbols. A is acceleration, omega is angular velocity, y is displacement, and the negative sign is very important because acceleration is always directed towards the mean position. Then the motion is simple harmonic motion. Then we can able to apply that equation E is equal to 2 pi into square root of m by k, right. Is that clear? So far, from the starting point here onwards, we have discussed about force constant, and we have obtained an expression for time period in terms of force constant, and we know the fact, right, through our discussion. To apply this equation to find time period of any motion, that body should be executing simple harmonic motion, and it is ensured by finding its acceleration A is equal to minus omega square y. If its acceleration does not satisfy this equation, then we cannot able to apply this equation to find the time period. Remember that on the basis of this, right, what I have written on the board, right, we will discuss oscillation of a loaded spring, as well as let us derive an expression for period as well as frequency of a oscillating loaded spring, right? Is that clear? Now, we have another concept, oscillation of a loaded spring. Oscillation of a loaded spring. With this discussion, we can derive the expression for time period of a loaded spring, right? Now, let us consider a spring of length L, original length L, and force constant or spring constant K, whose one end is right attached to a rigid support, and it lies along vertical direction, right, like this. I will show it in the figure. Right, this is figure 1. Now, this is the original length L, and it has a force constant or spring constant K. That K has two expressions. K is equal to F by Y. Remember, K is equal to F by Y, and K is equal to, right, M into omega square. This we have already discussed, right? Now here, when no load or any mass is attached to the lower end of the spring, there is no force that displaces the spring or changes the length of the spring, right? Therefore, in this case, restoring force, right, F is equal to 0. That means there is no restoring force, right? Now, this is the second figure I am drawing with the same spring. When a load of mass M is attached to the same spring, right? Now, the spring gets stretched. There is an increase in the length of the spring, right? That I will show in this figure. It is the load of mass M, right? Now, generally, in any case, the distance is always measured. Here, this is the original length of the spring earlier. Now, the length of the spring gets increased by a distance L, right? Now, this is the distance L through which the spring gets expanded or extended, right? Now, here what force causes increase in the length? It is the weight of that body or load that is attached to the spring. Whenever a displacement force is acting on the body, now that restoring force is developed in the spring, that restoring force F acts in the opposite direction of this force, right? So now we know that this restoring force developed in the spring is directly proportional to the displacement or extension produced in the spring, right? From the figure 2 we can write, right? Now restoring force, right? In figure number 2, F is equal to minus K into L. Let us take it as equation number 1, right? So, F is equal to minus K into L, where K is the spring constant or force constant and L is the displacement of the spring or the load, right? Now, here in this case, since, right, load M is at rest, here this is at rest and of course it is the mean position of the loaded spring. This is not, it is an ordinary spring without any loading. This is a loaded spring, it is attached to a load. Now there is an increase in the original length. When it is right at rest, then the center of gravity of this load represents the mean position of the loaded spring, right? Now since the load M is at rest, right? Now here weight of load is equal to restoring force. Weight of load is equal to restoring force. Weight of the load, that is mg, right, is equal to K into L. I am taking only the magnitude. The negative side is indicating that it is in right upward direction, right, that is opposite to the direction of displacement. Mg is equal to KL. I am taking only the magnitude of that force, right, because they are acting in opposite direction, right. Mg minus KL is equal to 0 or Mg is equal to KL or K is equal to Mg by L. This is equation 2, right. So the spring constant or force constant of the loaded spring is equal to mg by L, and of course if we go on increasing the mass, weight also increases, the length also increases, but the ratio of weight of the load to the expansion of the spring, right, always remains constant, and it is equal to the force constant or spring constant, right. And now here I will take the third case here. Now this loaded spring is held by the hand and pulled downwards, right. So now in this case the same spring when the spring is pulled down, right, now here there are two forces, right, downward, mg plus say delta f. Delta f is that force that displaces the load from its main position. Let this displacement be y. Now what is the restoring force? Already there is a restoring force F acting in upward direction. Now there is an additional force, right, delta F. Therefore again now the restoring force increases. Now the restoring force is F plus delta F. It is acting in vertically upward direction, right? Now the see here, again here is also rest, again here it is at rest, here also it is at rest. Is that clear? And now again with this one, now for figure free, for displacement y, when the load has displaced through a distance y from its main position, here the net restoring force is F plus delta F, and that is equal to, now for F the length is L, for delta F it is K. See here, in this case F is equal to minus K into L. This is F plus delta F is equal to, right, this length is L and this length is Y. This F causes this change in length L and delta F causes a change in length Y. So this can be written as minus K into L plus Y. That we can take it as equation number 3. I will take it equation number 3, right. Now subtracting equation 3 from subtracting equation 1 from 3, equation 3 minus equation 1, that is F plus delta F minus F is equal to minus K into L plus Y. Now see here, we have to subtract equation 3, equation 1 from equation 3, minus of minus, that is plus KL. I have written it is direct, this is minus of minus KL, that is plus KL, or therefore FF get cancel here, we will get delta F is equal to, this is minus KL plus KL get cancelled. Now we left with minus K into Y, that I will take equation number 4, right. Delta F is equal to minus K into Y. Now see here, this delta F, right, is equal to minus K into Y. Suppose if the load is released, then this delta F produces acceleration in the body and the load began to oscillate about its mean position. That is the mean position of the loaded spring. About this mean position it began to oscillate, that means execute simple harmonic motion, right. So if A is acceleration of load when it is released, right, it is pulled downwards and now I have released that load, then we have MA is equal to minus K into Y, right? MA is equal to minus K into Y, where M is mass, A is acceleration. Now this according to, right, Newton's second law of motion, that delta F is equal to MA. I can write, right? Right. Now this acceleration, therefore acceleration A is equal to minus K by M into Y. I will take it as equation number 5. So I found acceleration of the loaded spring is equal to minus K by M into Y. K, force constant, M, mass of the load, Y, displacement of the load from its mean position, right? But we have, right, omega square is equal to K by M. I have told you, remember this equation, right, while discussing the force constant. Omega square is equal to K by M. I have brought this from the discussion of force constant. Earlier we have done it. Therefore, A is equal to minus omega square Y. I have arrived at that equation 7. Right? What that equation 7? Equation 7 represents the acceleration produced in the loaded spring. Now, this equation is the acceleration of a simple harmonic motion. That means equation 7 indicates that motion is a simple harmonic motion. Motion is a simple harmonic motion, right? Now what is period of simple harmonic motion? T is equal to 2 pi into square root of, right, M by K. 2 pi into square root of M by K, right? Is that clear? Right. Then I will rub this part of this derivation, right, because I need some space here. Right. Now we have that period of simple harmonic motion. T is equal to 2 pi into M by K. But remember that, right, this equation 2, K is equal to mg by L, from equations 2, and this I will take it as E8. They are only just for convenience, that's all. Equation 4 and 8. Now the T is equal to 2 pi into square root of M by mg by L. This mm get cancel. Therefore, period of loaded spring T is equal to 2 pi into square root of L by G. So this is the expression for time period of a loaded spring, right, where L is the length through which the spring gets stretched when load is attached to the spring, right. Now this length, and G is a constant, that is acceleration due to gravity. Since 2 pi is constant, G is constant, T is directly proportional to L. Here we have to remember these two cases. How does period depends upon mass? T is directly proportional to square root of mass of the load, and T is inversely proportional to square root of the spring constant or force constant, and that we will discuss in the next class, right? So today in this class part 7 we have discussed two important concepts. One, force constant of restoring force, right, of a particle executing simple harmonic motion, and we have obtained an expression for period of loaded spring, that T is equal to 2 pi into square root of L by G. And another thing I would like to tell you, suppose I have a smooth frictionless horizontal surface with a rigid wall here. Now I have a spring. Right. So when a load is attached to the spring, right. Now when it is pulled rightwards, right, it began to execute, right, oscillation in horizontal direction, that is the horizontal plane. In this case also, right, this equation holds good, right. I mean, we can take directly T is equal to 2 pi into square root of M by K. Here this is M, this is K, then T is equal to 2 pi into square root of M by K. This equation holds good, right, even for a loaded spring, right, oscillating in horizontal direction. And one thing to be noted here, the horizontal surface is such that the frictional force F is equal to 0, right. So only on that basis friction is 0, there is no friction. Horizontal surface is a smooth surface offering no friction between the spring and the surface, horizontal surface. This equation holds good. T is equal to 2 pi into square root of M by K. So let us conclude this class, right, and you need to remember all those equations I have mentioned, equation number 1, 2, 3, 4, etc., which will help us solving numerical problems, most importantly in a competitive examination, right. So in physics, the questions in competitive examinations are 80 to 90% numerical problems, right. There you have to use formulae, apply your skill, right, and you have to solve that problem. So okay, we will continue in the next class, right, where we will discuss some basic things, right, the relation between time period, length, right, spring constant, etc. And one more thing we are discussing is, here I have used only one spring, right. When we use combination of spring, what do you mean by combination of spring? In spring, when we have used only one spring, how many springs are used in motor vehicles in the part of shock absorber? 2, right. Now even in cushion sofas and even some case of, right, beds, right, they are using that springs, right. Now those springs are several in number. They may be arranged in different ways, right? So if we use more than one spring, then what happens to the time period and how the time period depends then, right? Now here when we use the combination of springs, there will be change in the value of K, right? So for one spring, right, it is K. For several spring, we have to take the net value of force constant or spring constant, right? Okay, okay. We will continue in the next class. Thank you very much.